deadlines, because it just felt weird to have the review due this week when the exam was next week. It didn't feel right to me. So tomorrow is just section 6.6. We started it yesterday. We'll finish it today. And then on Saturday is 6.7 and 6.8. Those are both application problem sections. They're nothing but applications. So I'll be sending out lecture notes later today for both 6.6 and 6.8. And then on Sunday, a quiz 8. And the next Tuesday is the exam 4 and the review for the exam are both due on that date. And then on Thursday is the review for the final exam and the final exam itself. And again, you can start scheduling those at any time with ProctorU. I sent out the access codes for the final exam last week. It's a longer time slot, so make sure you use the correct access code for these two guys so that you've got the time you need for each of them. So, okay, well, let's go ahead and finish off section 6.6 on solving equations. Yesterday we did all the log equations. Today we're going to do the exponential equations. And again, we'll start off with stuff that we've seen before, which is really, really nice. So today we have 3 types, which is why I can't get it all into a single day. It's just too much. So type 1, you can make the bases the same. So usually there are some catchy titles for what we're doing, but I don't have any. So you can make the bases the same. And we did these last week, so it's kind of nice to start here. So in other words, if we have 5 to the negative x equals 25, and the directions are just going to say solve. So we want to solve that. So for this exponential equation, we know that we can rewrite both numbers as the same base. So the 5 to the negative x is already a base of 5. But the 25 is really 5 squared. So I can make the 2 bases into the same number. So once we did that, if you remember from last week, what we did is set the exponents equal. So once the bases are the same, you come in and set the exponents equal. And that was a property that we had that we used last week. So we're just going to make use of it again. And then to finish this one off, we'd have x is equal to a negative 2. So if you raise 5 to the negative of a negative 2 power, sure enough, you'll get 25. And we did those last week. They're going to look a little more complicated in this section than they did last week. So let's do one that's a little uglier than this guy. So what if we have 3, the 2x minus 1 equals 1 over 27. And again, the directions are just going to say solve. So I want to solve that. I want to find a value of x that makes this equation true. So we still can make the 2 bases into the same number. The left side is a base of 3. You always go to the smaller base because it's easier than going the other direction. I'm going to take that 27 and make it into a 3 cubed because 27 is 3 cubed. But I need to bring this up from the denominator. So we have 3 to the 2x minus 1 equals 3 to the negative 3. And now that our bases are the same, we can set those 2 exponents equal. So 2x minus 1 equals that negative 3. Again, setting our exponents equal. And then we can solve. So x equals negative 1. You'll notice that on neither the first example or this example did I bother to check, and you don't need to check these, and the reason is the domain for the exponential function is all real numbers, so there's no need to check. And that's because the domain is all real numbers. So there are no exclusions. You don't have to worry about negatives anywhere or anything like that. So those should go really quick because we've already done some similar to that. Comments or questions about type 1?
No.
Okay. Moving on to type 2. Okay, so type 2 for today. You cannot make the bases the same. So there's no way to make those bases into the same number. So we'll do a really quick case of this. So this might be 2 to the x is equal to 5. So 2 to the x equals 5. So there's no way to make a 2 into a 5, and there's no way to make a 5 into a 2. So I'm stuck. I can't do anything with that. Okay, so what you want to do in your first step is you want to isolate the variable term on one side. In other words, you may need to move things back and forth, and we'll see this when we start to do the applications tomorrow. I don't need to do anything here because the variable term, which is 2 to the x, is already by itself on one side, but just in case. Step 2, once we've done that, you can either call this two different things. You can either say that you're switching forms. I prefer to take the log of both sides because I think that's easier to do. So we're going to come in and take the log of both sides, which we've never done before, but because the log is an operator, you can do it to both sides. So we're going to come in and say log of 2 to the x equals the log of 5. And you can use any base here you want. So you can use base 2, you can use base 10, you can even use base e, you could use base 5. You can use any base you want. I tend to use the log of just base 10 because that's the easiest one to get to on the calculator versus a different base. So I tend to use log base 10, but you can use any one. The reason you're doing this is now you can move the exponents out in front. So now we're going to move the exponents. So what that means is on the left side, we'll use that power property to bring the x out in front of the term. So we now have x log 2 equals log 5. This is the only way we have of bringing the exponent out of the exponent spot. And since that's our variable, our unknown, we have to be able to move it. Now we're just going to solve. So step 4. At that point, we're in solve. So this is a little awkward. We just haven't looked at things that look like this, but this is x times the log of 2. So in order to get the x by itself, I'm going to divide both sides by the log of 2. So when it's all said and done, x is equal to log 5 divided by log 2. And that's your final answer. That again is the exact answer. Depending on the homework question, sometimes they'll want a decimal equivalent again. So I'm going to do log 5 and then divide it by log 2. And we end up with x is approximately equal to 2.3219. So 2.3219. Okay, now what you should be asking yourself is, wait a minute, if I can use any base I want, how can I always get a same answer as somebody else if I use a different base? So I think it's important to walk this through using a different base just to show you that, yes, it does work. So same problem, different base. Nothing's really going to change in terms of the work. But what we're going to do over here is we're going to take 2 to the x equals 5. And instead of using log base 10, we're going to use the natural log. So I have the natural log of 2 to the x equals the natural log of 5. I'll bring the x out in front again. So x natural log of 2 equals the natural log of 5. Then we'll divide. So x is going to be the natural log of 5 all over the natural log of 2. So identical in terms of placement of things, but it's a log base e versus a log base 2. And if you go to your calculator on this answer, because that change of base formula, you'll see it's identical to this one. So you'll get the same exact 2.3219. Which feels weird, but that's one of the properties of logarithms. So doesn't matter what base you can use any base, and in the end, the two decimal equivalents will be the same. Notice that the exact answers look different, but they're both correct, and the computer program should recognize both of them. Okay, now these are the ones that we're going to need more practice on. So let's go try another one. Is everybody kind of clear on what the steps are?
Yeah.
Okay. So we're going to come in and add in another variable. We'll put variables on both sides just to see how it works. So let's say we have 3 raised to the 1 minus 2x, and that's going to be equal to 4 raised to the x. So 3 raised to the 1 minus 2x is equal to 4 raised to the x. Okay, well, when you look at that, the first thing to note is that you cannot make a 3 into a 4 or a 4 into a 3. So you're stuck. So we're going to follow our steps. The variable is already by itself on each side, so there's no moving around. We'll do one of those in the next place, but I don't have to move anything around. I'm stuck. We're going to come in and take the log of both sides. Let's use ln this time, just to show in your notes that you can use either one. So I'm going to have the natural log of 3 to the 1 minus 2x equals the natural log of 4 to the x. And again, the reason you're doing this is the log is an operator. So it's something you're doing to both sides. The advantage is that now lets me move those exponents. So as I bring this 1 minus 2x down, I'm going to put it in parentheses to remind myself that I'm bringing the entire exponent, no matter how ugly it is, out in front. So then I have 1 minus 2x in parentheses times the natural log of 3. And that's equal to x times the natural log of 4. So now that I've done that, everything is now on the same line or level. So now we can just solve it. So what we're going to do is come in and distribute. So this natural log of 3 that's on the back side of the parentheses is going to get distributed to both terms. So I'll have a 1 times the natural log of 3 minus 2x times the natural log of 3. That's going to be equal to x natural log of 4. Which looks a little awkward for us. But again, ln of 3 is a decimal. It's an ugly decimal, and because I don't like writing out all those decimals, I tend to not write them in. I just carry it as the natural log of 3. Okay, now we're solving for x. X appears in this negative 2x term and this x natural log of 4 term. So I kind of want all of them on the same side. So I'm going to add 2x natural log of 3 to both sides. And that's what's really strange, is picking up that entire term and moving it over. But you can. So what does that then give us? Well, on the left side, I have 1 natural log of 3. That 1's a coefficient. I don't really need to write it. So I'm going to drop it here and just write natural log of 3. On the other side, we're going to have x natural log of 4 plus 2x, the natural log of 3. So I now have anything involving x over on the right-hand side. Okay, any comments or questions about that? These are some of the problems where it makes a lot of sense when I'm here directing the traffic, but when you go try them on your own, be careful. Now what are we going to do? Well, our x appears in 2 different terms, which does us no good. So we're going to factor it out. So I'm going to move up here. So I'm going to keep my natural log of 3 on the left side. On the right side, I'm going to factor the x out of these 2 terms. So if I pull the x out of the first term, I'm left with the natural log of 4. If I pull the x out of the next term, I still have the 2 and the ln of 3 that are left. So I have x, and then in parentheses, the natural log of 4 left from the first term, and the 2 and the natural log of 3 left from the second term. Since we're solving for x, the last step is always to divide. So we're going to come in and divide both sides by the stuff in parentheses. The natural log of 4 plus 2 natural log of 3 on both sides. So when it's all said and done, x is going to be equal to the natural log of 3 all over the natural log of 4 plus 2 natural log of 3. Okay, there's no canceling. There's really no cleanup. You don't need to do any cleanup on this. You can leave it alone. You're good to go. So this is their answer. You would take this to the calculator to get the decimal approximation. Be really careful about numerators and denominators. So if you go to the calculator, make sure you put that entire denominator in a set of parentheses. So natural log of 3 divided by ln of 4 plus 2 ln of 3. And be really careful. Make sure you close parentheses because the calculator puts them on the log terms no matter what. And I get 0.3066 is the decimal equivalent. And again, the book wants you to carry, I think it's 3 decimal places, 3 or 4. 3 decimal places. So if we round this to 3 decimal places, we'll go 307. Okay, any comments or questions about that? We're gonna do another one of these, but there's our first one.
I'm okay.
We're good? Okay, so let's get one that's just a little bit uglier. And then we can move on to our next type. Oh no, we still have to do 2 more of these, sorry. Jumping ahead of myself. Okay. So what if we have 0.3 raised to the 1 plus x, and that's going to be equal to 1.7 raised to the 2x minus 1. So the decimal of 0.3 raised to the 1 plus x equals 1.7 raised to the 2x minus 1. So each one already just single term on both sides, so we can skip the first step. The next step, we're going to go ahead and take the log of both sides. I'm going to go back and use log because I just want you to recognize it doesn't matter which log we use. So I'm going to do log of 0.3 to the 1 plus x equals the log of 1.7 to the 2x minus 1. Okay, the next step is to move those exponents out in front. So as you bring them down, write them in parentheses. So 1 plus x times the log of 0.3. That's going to equal 2x minus 1 times the log of 1.7. And the reason you put those parentheses there is they're going to remind you to distribute in the next step. So we'll come in and distribute the log 0.3 to both terms. And again, you're just distributing. It's just from the back side, which we're just not used to doing. So I have 1 times the log of 0.3 plus x times the log of 0.3. Whoops, don't lose my decimal. Okay, on the other side, again, we'll distribute that log to both terms. So we'll have a 2x log of 1.7, and then minus 1 times the log of 1.7. And I don't really need these ones that I'm writing in front of the log, and I'll drop them in the next line, but I want to make sure everybody recognizes that you did distribute, and that's part of recognizing that. Okay, well, I need everything that has an x on the same side. Everything else can go to the other side. So what I'm going to do is I'm going to take this x log 3 over to the right side, and that'll make this negative log 1.7 come to the left side. So we're going to take and move this guy this way, and we'll move this guy this way. That'll give me the log of 0.3 plus, as I move over that other term, the log of 1.7. That's going to be equal to the 2x, the log of 1.7, minus x, log of 0.3. So again, what I'm really doing is just collecting all the variables together. So the log of 0.3 plus the log of 1.7 equals 2x log 1.7 minus x log 0.3. We'll do the same thing we did last time. Let's factor the x out of that right side. So then I'll have 2 times the log of 1.7 minus the log of 0.3. I'm doing nothing to the left side, so it's just the log of 0.3 plus the log of 1.7. And then your final step is to divide by everything that's in the parentheses, and then you're done. So x is going to be equal to that log of 0.3 plus the log of 1.7 all over 2 times the log of 1.7 minus the log of 0.3. So, and there's your final answer. You cannot do any canceling top to bottom here. So don't try and cancel out these log 0.3s because they're separated by signs. You cannot cancel when you have those interior signs. So there is some cleanup you can do on these. And if I didn't have a calculator, I would clean it up a little bit more. So recognize that this too could come in as an exponent on the 1.7. Because this is a minus, you could rewrite this as the log of 1.7 squared divided by 0.3. The plus up here would make this into a product, but this is good. As an exact answer, that's fine. So, whew. And that's as ugly as they get. If you can do that, you will have no problem with the assignment whatsoever. Of which one of you has already done the assignment, so good job, because I had even lectured on the whole thing. So, okay, one more and then we'll move on to type 3. Okay, so one more of these. So what if we have 0.3 times the quantity 4 raised to the 0.2x, and that's going to be equal to 0.2. So 0.3 times the quantity 4 raised to the 0.2x equals 0.2. That's a lot of decimals. And because we're headed to those application problems tomorrow, you see a lot more decimals floating in all of a sudden. Okay, so we do have to do step 1. Step 1 was to isolate the term that had the exponent. So because this 4 has got this extra 0.3 out in front, the very first thing I'm going to do is divide out that 0.3. So I'll have 4 to the 0.2x is equal to, and I don't like 0.2 divided by 0.3. In general, you tend to not write decimals inside of fractions. So if I simplify this down, this is just the same thing as 2/3. So notice I'm not going to a true decimal until the very, very end. So it's 2/3. I multiplied the numerator and denominator by 10 just to get rid of the decimals. Okay, now we'll come and take the log of both sides. I'm going to use log base 4 just to be different and to show you that it works. So we're going to take the log base 4 of 4 to the 0.2x equals the log base 4, that is a 4, of 2/3. Why did I do that? Well, on the left side, when you bring the exponent out in front, you're left with log base 4 of 4. And what is log base 4 of 4? From last week?
1.
Yep, that's 1. So I just end up with a 0.2x equals log base 4 of 2/3. And then your final step is divide by 0.2. So part of the reason you guys don't like these problems is there's a little bit too much freedom in them. You would rather just have one way no matter what, but there's a lot of freedom in terms of how you approach these. So my final answer as an exact answer is log base 4 of 2/3 divided by 0.2, and that would be the exact answer. And then if I wanted to go to my calculator, I would have to go and figure out what log base 4 is underneath the math key. You can change the base on the logs. So we'll do a lot more of this manipulation when we solve the equations tomorrow and again on Thursday. So. Okay, but there's one more type. And these are actually some of my favorite equations all semester long, believe it or not. I like them because it ties together a lot of the stuff we've already done, so that's why I like them. So type 3 is going to be substitution problems. Okay. And how you're going to recognize these is by the number of terms. So I have 3 to the 2x plus 3 to the x minus 2 is equal to 0. So 3 to the 2x plus 3 to the x minus 2 is equal to 0. And the reason that this is different from the other ones we did is all of a sudden I have 3 terms. So I have a first term, a second term, and I also have that third term, and it's equal to 0. So it's definitely not similar to type 1 or type 2. What we are going to recognize is that the first 2 terms, the exponent on the middle one is half of the exponent on the front. And if you go all the way back to section 1.4, when we did substitution for the first time, you'll see that this is a quadratic in form kind of equation. So again, what's driving the conversation here is the fact that that's a 2x and that that's an x. So we're going to come in and let u equal the middle term, 3 to the x, the whole thing this time, not just the variable, the whole part of it. So by default, u squared would be u to the 2x. Whereas if I added 2 on this exponent, I have to add the 2 on that exponent. So when I rewrite this, this is u squared plus u minus 2 is equal to 0. So u squared plus u minus 2 is equal to 0. Okay, we're going to come in and factor this now because it's now quadratic. So that factors into u plus 2 and u minus 1, which is equal to 0. U equals -2. And u is equal to 1. At that point, we can unsubstitute. So I'll have 3 to the x equals a -2. And I'll have 3 to the x equals 1. And now we're back to the type 2. We now need to solve each of these little exponential equations, but the bases are not the same. So we're just going to come and take a log everywhere we can. I'll use ln. A lot of times it's quicker to write. So the natural log of 3 to the x equals the natural log of -2. And I'm going to finish that equation. That would be x natural log of 3 equals the natural log of -2. X equals the natural log of -2 divided by the natural log of 3. I was kind of waiting for somebody to stop me. Can I take the log of a negative number?
No.
Nope. So I really didn't need to do any of that. The minute I got right here and took the natural log of -2, I know that this one's no good. You cannot take the log of a negative number. And it should make sense. If you go back and take a look at this line right here, how can I take a positive base of 3, raise it to some exponent, even though the exponent might be a decimal? How do I raise it to some exponent and end up with a negative number? I can't. I can't take a positive base and make it into a negative number, so that one's no good. I can solve the 3 to the x equals 1. So we'll do the same thing, but over here now. So 3 to the x equals 1. So we're going to do the natural log of 3 to the x equals the natural log of 1. That moves the x out in front. That's why you're doing it. You can bring down the exponent when you take a log. And then we'll divide. So x equals the natural log of 1 divided by the natural log of 3. Now, I'm not quite done with that, but is everybody okay with that? You'll notice that the exponential part of this thing is not until the very end, right? This is just all quadratic stuff. Okay, can I simplify this even further? Well, what's the natural log of 1? 0. 0 divided by anything is 0. The natural log of 1 is 0. So the only way for this equation to be true is if the variable is a 0. And sure enough, 3 to the 0 power would be 1. 3 to the 0 power is 1. 1 plus 1 is 2. 2 minus 2 is 0. So yes, it does work. So I like the substitution problems. I don't know why I like them, but I do like them. I think they're kind of fun. Okay, let's do one more. You have 2 on your homework, so we'll do 2. Comments or questions about it?
I'm okay.
You guys are kind of quiet today.
No.
It's not even a Monday morning. It's a Tuesday morning and you're quiet.
What happens if both sides are negative?
No, then there's no solution. And that can happen. So when you factor, you might factor something that they're both negative. Yeah, so you'd have no solution because it can happen. It's a good question.
All right.
Thank you for asking a question. So I have 2 times 49 to the x plus 11 times 7 to the x plus 5 is equal to 0. So I look at that and I freak out a little bit. We're going to notice that we have 2 different bases raised to powers, but 49 is the same thing as 7 squared. So I'm going to rewrite this as 2 times 7 to the 2x plus 11 times 7 to the x plus 5 is equal to 0. And now I feel more comfortable with it because I can see the 7 to the 2x and the 7 to the x sitting there. So we'll come in and do our substitution. So we're going to let u equal the 7 to the x. So the first term becomes 2u squared plus 11u plus 5 is equal to 0. And now we're going to factor that. So 2 times 5 is 10. Factors of 10 that add to 11 are 10 and 1. So that's going to factor into 2u plus 1 and a u plus 5. And again, if you still don't like factoring, you could take it to the quadratic formula. Just make sure you go all the way with it. So this will give me my 10u. This will give me my 1u to get the 11 out of the middle of it. So we're going to end up with u equal to a -1/2. So your question was really, really good because here it is, right? We're going to end up with u being 2 negative numbers. So 7 to the x would be equal to a -1/2. 7 to the x would be equal to -5. So in this case, it is no solution because you can't solve either one of them because of the negatives. So that was a really good question. You led us right into the next example. Okay, and that's the rest of the solving in section 6.6. So you now should be able to do all of 6.6. We'll start 6.7 tomorrow. And again, I am going to send out lecture notes because they're all application problems, and that way I don't have to write too much on the board tomorrow. And that way you will have them. Did you guys go off and think about anything that we could do to make the synchronous online? I think there's all kinds of different ones. Somebody called it a flex hybrid. I have not heard that term, but we call it synchronous online in the math department, meaning you're getting a lecture that is live at a specific class time, and then the majority of the rest of the class is online or with something submitted. So what would have worked better for you? Suggestions? I have my Post-it ready to write on.
I submitted mine, but I racked my brain for about half an hour and I couldn't think of anything better.
Okay. Well, and that tells me a lot. It really, really does. So that's good. Adam, anything we could do differently to make it the class in general work better?
I don't know. I haven't done mine yet. I'm thinking about it.
Okay. Okay. And the only reason I'm harassing you guys today is because the department meeting, the department chair is going to ask me, because I've done the synchronous online over the summer, what would be suggestions that I would pass on to the department. So there are 3 of us that are doing it this summer, and each one of us is going to get put on the spot to try and, help everybody else for the fall. So Matt, any idea?
Well, it's been good. It's just probably put on a little add-on and a roll call, make it easier for the school to see who was in the Zoom class, and that's it.
Correct. So I have not figured out. It's easy because right now there's just the 4 of you, but my applied calc class in the fall has got a class of 30. So right now on the side of my screen, when I'm looking at it, I can see the names of the people. But if there are 30 of them, trying to keep track of the roll call is going to be difficult. So now I can look over the meeting in Zoom, but I haven't found a way to figure out how I look at who's participating. So that's a good idea, how we're going to take roll or attendance, right? Anything else? Christina, can you think of anything?
Just ProctorU. Sometimes it takes forever, or there's like glitches. It takes a long time to get onto my exam.
Correct. So would it have worked better? Because I can do a browser lock in Pearson. So in other words, when you have My Lab Math open on a test, it locks your browser down and you can't look at anything else on that computer. Doesn't mean you can't go use your phone, but on the computer you're working on, you cannot go to anything else. So I can use a browser lock. So my thought would be, if I were to do an actual online exam again, would be to lock the browser and then have students use their cell phone as the camera, so that I know that the camera is working over here, you're doing this over here, and there's no way for you to be looking anything up. So you wouldn't use ProctorU, would you?
No.
Okay. What about you, Matt? Would you use ProctorU? Okay, Rich?
Well, I'll use it to ensure, to show everyone I'm not cheating, but it's kind of weird just.
Correct. Yeah, I personally am going to use take-home exams. I'll use the quizzes online. I'm not worried about the quizzes, but for my class moving forward, I'm just going to use take-home exams. That's going to work best, I think, for me. So if you were to miss a day and not be at the Zoom lecture, would you physically go and look at the YouTube video or not? Because I'm not seeing a lot of people using the YouTube. You would?
Yeah, I would.
Okay.
Yeah, I would.
Yeah,
I definitely would.
Okay.
I wouldn't watch the YouTube video when I went to work this morning, so.
Okay. Okay. So that is worth doing then, because the one person who cannot attend the Zoom lecture is not really looking at those videos. Because I'll have no visits, right? So I know that nobody's looked at that one, right? Sometimes I'll have 1 visit, sometimes 2, but not looking at all of them. So, okay, I think that gives me enough to be able to talk to the department in general. So, okay, so I think we're good to go. So again, I did change the due dates. I sent out an email, and again, I extended them is what I did. So it didn't move anything forward, it moved things back. So you guys have a great day. Any other comments or questions?
I'm good.
No.
Okay, have a great one. Enjoy it. Enjoy our hail and rain this afternoon.
All right. Bye.
Goodbye.